In this video, we continue with chapter 5.3, and we are going to explore orthonormal bases, and we're going to see how to represent a vector relative to an orthonormal basis. So this is an example of an orthonormal basis in R2. We've got W1 is a projection of W onto I, the unit vector here, and W2 is a projection of W onto J, the unit vector in the second dimension, or what we think of as the y-axis. And so any vector W in R2 can be represented as a combination of this, W equals W1 plus W2, where again, W1 down here on the horizontal axis is a projection of W onto I, where remember I is 1, 0 in R2. And then W2 is a projection of W onto J, where J is this unit vector 0, 1 in R2. All right, and then we can show this by saying, okay, well, we can break it down. So we've got W equals W1 plus W2. Well, we can say, well, that's just W dot I multiplied by I, where W dot I gives us that coefficient of how it's stretched by, plus W dot J, that, inner product, or in this case, a dot product because we're in R2, gives us a value, a scalar, a coefficient, multiplied by J. So we're going to have this scalar that we'll call C1I plus the scalar that we'll call C2 multiplied by J. And so these scalars, to find the scalars, you just take W and dot it with I or dot it with J. And so let's take a look at the next theorem, which is going to generalize this. So in any inner product space, if B is the set of vectors V1 through Vn, and it's an orthonormal basis for an inner product space V, then the coordinate representation of a vector in W relative to B is going to be the inner product of W with each element V1 through Vn multiplied by the vector itself V1 through Vn. So see, I've got W inner product with V1 here, and then that gets multiplied by V1. So these are going to be like our scalars here. And so we can call them, if we want, C1 through Cn. So it's the coordinate representation of any vector W, because remember, any vector W is going to be able to be constructed through this basis V1 through Vn. All right, so here's the proof. We're going to assume B is a basis for vector space V. So there's got to exist these scalars C1 through Cn that are going to be unique, where we can write any vector W as a linear combination of them. So C1 V1 plus C2 V2 added all the way through Cn Vn. So now taking the inner product with Vi, where I is going to be that index that's going to go 1 through n, of both sides of this equation, so W inner product with Vi is going to equal our C1 V1 plus C2 plus V2 all the way through plus Cn Vn inner producted with Vi here. And then we can pull the constants out we know by properties of inner products. So we can pull out C1, C2 all the way through Cn. And then we've got, V1 inner producted with Vi, V2 inner product with Vi, all the way through Vn inner product with Vi. And then because B is an orthonormal basis, these are all going to zero out except for when you've got Vi inner producted with itself. So on the left side, the W inner product with Vi is just going to equal the scalar Ci multiplied by the inner product Vi with Vi. And so B is orthonormal, so we know the inner product of Vi with Vi is just the norm squared of Vi, and that's just 1 squared or 1. So then it must follow that our scalar here is found by the inner product of W with Vi. Or in other words, W inner producted with Vi is 1 times Ci here. So I'll put the Ci first. So it's going to be Ci multiplied by 1. And so that's just Ci. So that's where this formula is from. All right, and then in theorem 5.11 back here, the coordinates of W relative to the orthonormal basis B are called the Fourier coefficients of W relative to B, after Jean-Baptiste Joseph Fourier, this French mathematician that came up with the Fourier series and some other great calculations. So the corresponding coordinate matrix of W relative to B, we could write it as, our coefficients are our scalar C1 through Cn transpose, which is just a column vector. But then what that's saying, well, if you don't want to think about them as scalars, you could think about them as just the inner product of W and V1, W and V2, all the way through W and Vn. So this is just an alternate way you can write those, and they're called the Fourier coefficients. Okay, in this example, let's find the coordinate matrix of W, and W is going to be the vector -2, 6, 5, relative to this orthonormal basis here. 1/√2, 1/2, 0, negative root 2 over 6, root 2 over 6, 2 root 2 over 3, and then 2/3, -2/3, and 1/3, all in R3. So I'm going to write out this solution for us. All right, so I got to do some dot products here because we're in R3. That's our inner product. Yeah, I'll switch to the black color. It might be easier to read. So my first dot product is W dotted with V1. So W is -2, 6, and 5 dotted with V1 is the 1/√2, 1/√2, and 0. All right, so if we work all this out, and you can double check my maths, we're going to get 2√2, because you can see you're going to get a -2√2, -2/√2, plus 6/√2. That last term is just going to be a 0. So you get 4/√2, which we like to rationalize to 2√2 to look a little bit nicer. All right, then W dotted with V2, I'll switch over to blue here, is going to be -2, 6, 5. And again, I'm using the dot product because I'm in R3, and that's our Euclidean, our standard dot product in our inner product in R3 is the dot product. All right, then I'm going to have -√2 over 6, √2 over 6, √2, 2 times √2 over 3. And then you can check all the steps here. You're going to get, let's see, you're going to get a 2√2 over 6 plus just a √2 because the 6's are going to cancel for the next term. And then you get a plus 10 √2 over 3. So this all actually ends up working out to be 14 √2 over 3 when you convert the 2√6 to a 4 over 3. And then our last calculation here for W dot V3 is going to be -2, 6, 5 dotted with 2/3, -2/3, and 1/3. All right, so we're going to get what, -4/3, -12/3, so -12/3, and then +5/3. So you end up with -11/3. And so our coordinate matrix is going to be, I'm going to have to write it as a transpose instead of a column because I don't have enough space down here at the bottom. It's going to be 2√2, 14 √2 over 3, and negative 11 over 3. And I'm going to put a transpose here because if I had more space, I would have just put it like in a column matrix like this. So you can either write it as a row matrix and put a transpose on there, or a column matrix. So that is our coordinate matrix. And those values correspond with the coefficients that you would multiply V1, V2, and V3 by to reconstruct W. Okay, in the next video, we are going to learn a procedure called the Gram-Schmidt procedure for finding an orthonormal basis. So we will pick up here and I will show you how you can do the Gram-Schmidt procedure by hand and in SIMPy.